Hello, everyone. I'm Dragoie with Chinook, and with me is Sergey Lebedev with Rogii, the makers of StarSteer. And today's presentation is going to be about resistivity modeling and its use in McMurray thermal wells development. Thank you for attending, and I will pass it over to Sergey to begin with.
Thank you, Kaylin. We'll be talking about propagation resistivity as it's different, for example, to lateral lock resistivity. It has much bigger depth of investigation compared to gamma or neutron density logs. Though it's quite deep, the resolution of the propagation resistivity is quite low, and almost none of the logs that can be obtained from the resistivity tools tell you the true formation resistivity. Moreover, many vendors have their tool specifications with different spacings between transmitters and receivers. You'll get both attenuation and phase shift resistivities from the tools, and maybe at different frequencies. And you need all or some of those logs in order to interpret effects happening in horizontal wells and see where information the well is placed. Right, so all those effects, in order to correctly interpret, need to be modeled. But because of different tool specifications, tool vendors used to do the modeling by themselves. And in the Geosteering and Geoscience package StarSteer, we added universal algorithm that works with the majority of the tools available on the market. So it's a vendor-neutral algorithm, and any operator or independent service providers can use it. Basically, resistivity forward modeling is when you have a model, populated properties along horizons taken, let's say, from an offset well, and the software calculates log responses that can you either to compare with the actual logs, or you can use them for pre-job modeling in order to see which log responses you should expect. Another approach is resistivity inversion. It's when you have the logs and run the inversion to map a boundary. It's not always the case and works well, for example, in Clearwater formation, but in the SAGD wells placed close to the oil water contact in transition zone, the forward modeling works better, which Kellen will show to you later. In StarSteer, we support a huge list of tools and vendors with more than 10 vendors and more than 25 tools. On top of standard resistivities, we added the capability to run the forward modeling of azimuthal deep resistivity tools such as AziTrack by Baker Hughes and GuideWave by Weatherford. We're planning to add Periscope and ADR tools by the end of this year. So I'm passing the presentation to Kaylin for the actual showcase.
All right, thank you, Sergey. We have a better understanding of the underpinnings of the software now and how that all ties into resistivity modeling and inversion. As you mentioned, as Sergey mentioned, we will talk mostly about resistivity modeling and how that applies to specifically the McMurray reservoir. And to give you a little bit of background, we talked with Rogii about resistivity modeling for probably a couple of years now, and it sparked our interest from the beginning. We tried traditional geosteering with curve correlation in the McMurray, and it has poor results for the reason that are outlined here: variable lithology, variable thickness, inclined stratification, you name it. IHS is breccia, unconformed boundaries, oil-water contact that is not always flat. You have it all here. So we tried this traditional geosteering in McMurray. It doesn't work. Resistivity forward modeling, on the other hand, I believe holds the key to unlocking geosteering for oil sands reservoirs such as the McMurray, not just for us, but for any operator that is active in this play. So we jumped at the chance to test this approach when Rogii released the first working installment last year in the fall. We demonstrated this and refined the workflow on a couple of projects, most notably with CNRL in the fall of 2019, at that time using Weatherford LWD tools. And since we demonstrated this approach with by using Halliburton tools, Weatherford tools, Schlumberger tools, and as Sergey mentioned, that's as vendor neutral as it gets. Now for this presentation, I will demonstrate the workflow using Geosteering with resistivity forward modeling. We'll look at the software capabilities, and then we'll take it a step forward by looking at the combined models and the potential advantages of this method and its application in the McMurray. So for this presentation, we did not use data that we or a project that we geosteered in real time, but we looked at the legacy data. Our data set, we used the publicly available data, got it from PetroNinja. We got well information, surveys, LWD curves, offset logs, covering Statoil's oil development in Leismer. That's around township 7810. This acreage now belongs to Arabasca Oil. This data set covers delineation wells, producers, injectors, and infills, and they used the Halliburton and Baker Hughes tool. That was part of the appeal of this data set. So let's jump right into the geosteering flow workflow. Part of the prep work is generating squared logs based on resistivity curves logged in delineation wells. And we do this for a couple of reasons. One is simplifying the base model to increase computational speed, and also to achieve a more constant resistivity profile across the well bores of the producers in this case. The log squaring submodule of StarSteer allows us to pick a curve object from the type well, and generate a square log, then tweak its contacts and bed thickness. And this simplified resistivity profile, this spin curve here, will be used to generate an earth model. That's the next step. And let's see how this actually works in the software. And there's a video here. Start it. There we go. And we carefully select a few type wells along our well bore. And then we pick a resistivity module in StarSteer and proceed to the log squaring submenu. Then we pick a resistivity log from the list and we create a corresponding square log. We adjust that, we adjust contracts and bed thickness, we adjust color thickness and scale, and we repeat that process for additional logs. We can use as many logs as we want here. That's all the formatting and all the thicknesses changes, and repeat that over and over for as many wells as we need. So we end up with several squared logs here. And that's the first step in using this, the first step of this workflow. The next step is creating earth models. We create these earth models based on the squared logs that we created in the previous step. Earth models are what they are 3D matrices of resistivity values positioned in a vertical scale depth and along the well path. They are calculated from these squared logs. This is what the raw data looks like. We calculate them from square logs for simplicity reason, but they can be calculated from any log. Earth models are objects inside these our interpretation, and any interpretation can only have one earth model. Specific earth models can be updated to reference one or another squared log. And the StarSteer can work with multiple interpretation, as we know. Each one has its own discrete earth model, though. And as we'll see further, earth models can be combined to show different profiles or more than one profile along the well path based on changes in stratigraphy and what the closest offset is. And let's see again if we can demonstrate this on the actual software. what we do is we create the horizons as we usually do when we start an interpretation. We paint those horizons based on the Earth model to have better visuals at this point. We can use whatever we want there. And this Earth model is automatically created when we start an interpretation, but we can always update it based on any square log that we pick. So we end up with this Earth model with its own matrix of resistivities. What this is used for, and we'll see in the next step here, is modeled resistivity logs, or what Sergey mentioned as forward resistivity modeling. And this is where the setup pays off here. It's a separate submodule, and it's used to generate simulated resistivity curves based on a theoretical response of specific tools used in the well when we drill through the Earth model that we created. Now, what goes into this calculations are well trajectory, angle of incidence, bed thickness, tool specifications. These are all parameters that go into the computation, relatively complex, I'd say. The generated simulated curves that we'll see here will be compared to the actual LWD response. And let's see here how this would work. We select the forward modeling submodule. We pick the tool string corresponding to the LWD provider that we have. And in this case, it's Halliburton. We pick the curves to correspond with the LWD curves available. Then we generate the simulated curves. This we would format, display them where we want. And with this, we will be ready to geosteer. It's this pair of red curves versus the registered or the recorded blue curves. Simulated curves red, recorded curves blue. Now we're also ready for actual geosteering. And we'll go to the next step. This interpretation that we're going to look here is a single model. We'll explain the difference between this and the combined model later. So we look at an interpretation using a single well profile, one of these wells, where the resistivity profile is considered uniform along the entire well length. We just have the one resistivity profile. The correlation is visualized along the measure depth track. And this is achieved by tweaking horizons at block boundaries. We just pick this point, drag them up or down to simulate the location of the well path inside our geology. And let's see how this works. That's the geosteering. We switch to geosteering mode now. We create block boundaries. We tweak the stratigraphic position while simulated curves are recalculated in real time. We also tweak block boundary position to achieve better correlation. And then the simulated resistivity is recalculated all the time. There's no buttons to push. And these calculations are based on well path position, Earth model resistivities, and the tools selected. What we want to achieve is the correlation between these red simulated curves and the blue LWD curves. Now, going a step forward, we're going to talk about combined Earth models. I'm sure that the software will do this in a more user-friendly and automatic way at some point. Right now, it's a little bit more cumbersome and labor-intensive. But what we can do is this: with any interpretation that has a single Earth model object is restricted to just the one profile. So we can combine multiple well profiles and achieve a combined Earth model. The process, as I said, is a bit more laborious, but the resulting Earth model used is potentially much closer to the real reservoir geology, and it will reflect the variable nature of a play such as the McMurray. Different resistivity profiles are reflected in this Earth model, and these differences will be used to generate the simulated resistivity response, or the forward resistivity. And this is how it would look like. What we have here is different simulated resistivities based on different Earth models. For each individual stretch of the producer, or an infill well for that matter, for the wells that we analyze, we do separate interpretations with corresponding Earth models, just like we would for with a single Earth model, but now we do it 4 times over in this example. This model is then stitched together, and the resulted simulated resistivity curves reflect the profile chosen in distinct areas of the wellbore from that combined Earth model that we've seen before. During the geosteering step, the combined Earth model is used to generate these red modeled resistivity curves. The best scenarios are picked by adjusting block boundaries within the Earth model profiles, and the combined Earth model is reflective of the changing lithology as seen in different delineation well along the well path, wells with distinct resistivity profiles. And this would be the equivalent of using multiple type wells in a traditional geosteering interpretation. We're using all that information along the well path to generate more simulated resistivity curves that are closer to the geological reality. And this is just another example, just a quick recap of the combined Earth model approach. We have separate squared logs generated from separate or multiple offset wells. Each squared log is used to generate a distinct Earth model. Then these Earth models are combined, stitched at the appropriate spot along the lateral. And then the simulated forward model, the resistivity is calculated based on this combined model. And of course, taking into account the tool string, the stratigraphic position, the relative inclination. We tweak that in the geosteering step by using the combined model for curve correlation of simulated resistivity curves and recorded LWD curves. Just as a summary, these are some of the steps that go into a geosteering interpretation and preparation, including mapping, top picking, display setup, formatting, colors, all that, and then resistivity forward modeling specific steps like log squaring, Earth model generation, the tool and the curve setup, tool picking, of course. It's all done prior to the geosteering and curve correlation. This curve correlation step is where we spend the most of our time as geosteerers. And we do this in order to project targets ahead of the bit in a real-time geosteering scenario. For this, we use calculated apparent dips and the standoff determination with resistivity correlation. Now, this particular project, we used it also as a training ground, and in addition to develop a few interesting workflows. And that was related to data loading, automatic calculation, data analysis, batch processing, exports. I would like to take this opportunity to thank our team of geosteerers, Wana Katlak, Adrian D, and TB Marcus. They helped a lot with expanding the scope of these projects from a few demo wells to an entire pool with the 7 pads here. I would also like to mention another workflow, infill planning. This was a separate workflow that we developed, and this was to be deployed in planning infill wells, where we would average geosteering interpretation of adjacent wells to simulate expected resistivity response at different directional planning scenarios. We used this with CNRL last year, and real world results, like the recorded curves, were very close to the simulated response. that's not surprising. So we know it works. Also wanted to mention that by using this system, we get the usual advantages stemming from the powerful integration of Python scripts into StarSteer. And that's analysis of large data sets, fast custom calculation, statistics, and not to mention the shared data access that comes with it. I will leave it at that, and we will welcome questions. Thank you.